But of course, this RADC comes with its own set of problems. But like I say, only if you have problems, as engineers, you have jobs, right? So let's look at what are the issues we might have and how we tackle it in practice. The first issue is this. So loosely speaking, in a sorry, no, there are. That's what we are coming to. So first non-ideality we might face is this. So in a SAR ADC, right, we know first we are sampling the input, and after sampling, okay, in a differential SAR we compare with the reference of 0 first, and then we compare with Vref by 2, right, plus or minus Vref by 2. That's okay. So the first comparison we do is with Vref by 2, right? So loosely speaking, I have a bunch of capacitors, and this voltage must charge from 0 to Vref by 2. I mean, even the switching scheme that we saw, we put in an initial condition of Vin minus Vref first, and then we want the voltage to go to Vin minus Vref by 2. Right? So which means along with this voltage, I have to add an additional Vref by 2. Right? Is that okay? So if I forget this initial voltage, I can think of it as though the capacitive DAC here has to charge from 0 to Vref by 2. If I ignore the initial condition here, right? And we used switches for switching the capacitors. The switches will have their own on resistance. So it won't jump instantly from 0 to Vref by 2. It will do a slow exponential settling like this. So what can happen is, let us say when the comparator is looking at the input, let us say the voltage has not settled to Vref by 2 fully. So instead of comparing it with Vref by 2, we might compare with a smaller value. Okay. It is, yeah, it's not an offset as such. We'll see that, right? So what will happen is this. So ideally we should be comparing with Vref by 2. But now let us say, because this is called DAC settling issue, because the DAC has not settled completely, we might compare with slightly smaller value. Now let us say your input is somewhere here. Ideally the output of this comparison must be 0, right, because input is smaller than ideal reference, but because we have only charged to this voltage, this will give an output of 1. Right? So let's see what will happen because of this. And this actually could be a problem in asynchronous operation, because we are doing it in an asynchronous fashion, right? So first what we do, we generate a valid signal, and then using the valid signal you generate these clocks and save the data, and then you switch the capacitors here. And remember, parallelly the valid signal is also used for resetting the comparator. So it can so happen that by the time we start the comparator, this guy has not settled fully. Okay, is that clear? So this is a problem, especially in the first step, because in the first step we are jumping from 0 to Vref by 2. That's a huge jump. Okay, so we'll see what will happen because of that. And for that, let's actually look at a 4-bit SAR. So this is a 4-bit SAR. So you can see 4 comparisons. So first we jump up by 8 steps, next 4, 2 and 1. So let's assume that we have an input close to the middle reference voltage. Ideally this is the code we should get, 7. Now let us say I compare with the first reference voltage. So let us say because the DAC has not settled to the correct value, or because of some other reason we make a wrong decision. Ideally from here, should we go up or go down?
It should go down.
Should go down, because the input is smaller than the reference voltage, but we make a mistake. So let us say we go up. So now we compare with this guy. We'll go down, because you see this is actually much farther from the input, and we have given sufficient time, so settling will also be not a problem, right? So second comparison will be fine. So we come down, here we'll again come down, and then we'll end up here. So instead of reaching the correct code 7, we end up at a code 8. So that's a problem, right? So if you see any error you make in one of the MSBs, that keeps propagating throughout the end of the conversion. So this is going to be a problem, so we have to tackle this.
Plus minus 1.
But if you plus minus 1, yeah. So the solution, I mean, you can actually take inspiration from the way you solve your exams in practice to solve for this. So here, what's happening? Oops. Just a second. Let me just copy paste this. Yeah. So here, right, we have 4-bit SAR. It is doing comparisons in how many steps? 4 steps. So let us say you are writing an exam which has 4 questions. Let us say first question is very difficult. So you know there is a good chance that you might make a mistake in the first question. Let us say you finish all 4 questions. You see the time, you have a lot of time. What do? You again go back and check the first question. We'll do something similar here. So what we'll do, we'll not trust the decision we made initially. So we'll go and recheck this level once again. Now the natural question to ask is, well, in the first time if I made a mistake, how can I be sure that the second time I'll do it correct? In the SAR case, it's okay because the first time you had a very short time for settling to VREF by 2. Now if you compare it at a later time, you have given enough time, so hopefully things are okay. I mean, the same analogy in exams, right? First question you are solving, you might be in a, like jittery, your mind might not be calm, you might make mistake. After some time you relook the same question, you hopefully will be able to solve it. The same analogy extends. So we'll do something like that. So which means if I have a 4-bit SAR, nominally I should do 4 comparisons. But if I were to correct for an error, how many comparisons I should make? At least 5. Right? So I should do more than 4 conversions or comparisons. So this is usually called redundancy. Because
you are assuming only in the MSB you will get.
Because that is the most crucial thing, because the settling there is huge, right? You have to jump from 0 to VREF by 2. Isn't it? This is where you can make a lot of error. So this is called redundancy because nominally if there were no error, you can finish the comparison in 4 steps. Now because of error you are adding redundant comparisons. So before going to see how this redundancy can be implemented in a SAR, let's understand it at a slightly higher level. So let us say here we have a 4-bit. So we first jump by 8 steps, next by 4, 2 and 1. So in terms of circuit implementation, we ground the 8C capacitor to ground for switching by 8 steps. For switching by 4 steps, you ground the 4C capacitor to ground and so on. This is how it translates to circuit implementation. Okay. So now let us say I made an error in the first comparison. So instead of going down, let us say I went up. In how many steps I am going in the wrong direction? By 4 steps, right? So I am going in the wrong direction by 4 steps. Now let us say I have to correct for this. I should keep coming down after this. That's the only way I can correct for this error. Clear? So let us see by how many steps I can come down. So from here, I can come down by how many steps? 2 steps. And again I can come down by 1 step, that's all. So total number of steps I can come in the correct direction is how many? No, 3. But I went up in the wrong direction by 4 steps. And the number of corrective steps I am taking is smaller than the number of steps I went in the wrong side, and that is why I am not able to correct. Okay. So let's say I generalize this. So let us say the weights I have here are W1, W2, W4. Now let us say I made an error in the first step. The number of steps I go in the opposite direction in the wrong side is what? No. I made an error in the first step. I go in the wrong direction by how many steps? 4 steps is W2. Isn't it? So I go in the wrong direction by W2. And the number of steps I can go for correcting this is what? W3 plus W4. And as of now, this is not enough. So, which means we have to add an additional step here for redundancy, something. So, the total number of steps I can go in the correct direction to correct for the error is what? sum of all these. Okay, and if I were to be able to correct for the error, this W3 plus W4 plus the end, how should this be in comparison to W2?
Equal.
At least be equal, if not greater. So the number of steps I go in the wrong direction must be smaller than the number of steps I go for correcting it. Is that okay? So this is the number of steps I am taking for correcting the error. That should be greater than or equal to the number of wrong steps that I had taken. Okay. So if I were to generalize it, it will be summation I. This is W2 3 to n. Okay. So this is the condition to have redundancy in the first step. That is, if I were to if I have to have a case wherein even if I make an error in the first conversion, I should still be able to correct for it. The condition that I have to satisfy is this guy. Is that clear? So let me actually copy this. So let's generalize it, right? So let us say I want to find the condition for having redundancy in the kth step. By this I mean that even if I make an error in the kth comparison, I should be able to correct for it towards the end. So what do you think the condition might be for this? This is for the first step. Yeah, summation I, this should go from k plus 2 to n, wi, that must be greater than or equal to k plus 2. Okay, so this is the condition you have to satisfy if you need to ensure that any error made in the kth step can also be corrected, right? And if you actually, let us say now we have 8, 4, 2 and 1. Let us say you decide to add one more step here. But if you follow a binary weighted scheme, so after 8 we have 4, 2, 1. What will be the next one?
0.
No, we have to follow a binary weighted scheme. 1 by 2, 0.5. Let's say I add 5th step in the hope of correcting it. But I follow a pure binary weighted scheme. You cannot reach it, right? Because you see, if I were to have redundancy here, some of these guys must be greater than this. That doesn't happen. That's simply because the binary number system has no redundancy. Okay, so if we were to introduce redundancy, you have to break this binary pattern. Okay, and in practice there are several different ways in which you can do this. I'll just discuss one technique which is simple and more efficient. And what we do there is this. See, in a 4-bit SAR we have weighting factors as 8, 4, 2, 1. So the total weight is what? Sum of all these?
2 power.
No, sum of all this is what? 15.
15 to power n minus 1. Power n minus.
Yeah, right? So now what we can do is, and remember that these weights are implemented in circuits. How are we implementing these weights in circuit?
4C, 8C.
We have a capacitors 8C, 4C, 2C and C. Right? Now one way to introduce redundancy is to keep the total Wi to be same. You keep this to be same, 15. But distribute this total weight of 15 in more than 4 steps. So that you meet this condition. This is nice because in that case you don't need to increase the capacitance you need, right? You keep the total capacitance as 15, same as a conventional SAR, but you distribute those capacitors in different weights so that you satisfy the condition for redundancy. It is the same, right? You have, usually we had 8C, 4C, 2C and C, right? Now what we'll have is something, let's say C1, C2, C3, C4, you will have one more C5. You will compare for 5 times or 6 times. So there are again different ways in which you can do this also, and one way is this. So let us say I take this 8, 4, 2, 1. I split this 4 as say 2 plus 2. And I will say the weights I will have are 8, 2, 2. That is one way in which I can do. Right? The total is still 15. Now I have 5 steps. So hopefully I will have redundancy. Let's check that. So let's see, we have redundancy in the first step, right? So in the first step, if I should have redundancy, what is the condition?
It goes up.
So if I were to check here, I should look this guy. This is the number of steps I can take in the wrong direction. This is 2, and the number of corrective steps I take is this. So 5, the corrective steps I can take is 5, the wrong steps is 2, which means I definitely have redundancy. Let's see, we have redundancy in the second step. So I'm looking here now. The number of wrong steps I can take here is how much? 2. Okay. Now, number of corrective steps I can take is greater. So I should still have redundancy in the second step also. Let's check that, right? But let's say third step, the wrong step I can take is 2. Correction I can do is only 1. No redundancy in third step. So let's verify that. So this is the weights I have. So this is the trellis. So let me write the weighting scheme. So 8, 2, 2. Okay. So as you see here, we have 5 steps. First step, second, third, fourth and fifth. Right. So first I jump up by 8 steps. Next step I jump by 2, 2, 2 and 1. This is the weighting scheme. And okay, let's see. Yeah, and as you see in the first step, we are comparing with this reference voltage. This is again getting rechecked again. That's why we have redundancy in the first step, right? Now similarly, we have redundancy in the second step also. So these are the levels with which the second step is usually compared. So that is why we have redundancy here. Okay. So let's quickly see if it works, right? So this is, let us say, same input is here. I compare it, I make an error. Say I go up. Output of this comparison is 1. Now I compare with this. It should come down. Now again I compare here. Now hopefully I have had enough time that I should be able to do a correct decision here. I'll come down here. Now what will be the step I take? Go up. And then last time I end up at the correct level. So if I were to write the binary output, not binary output, the digital output I get 1, 0, 0. Right, this is what I get. Now remember that this has to be decoded as 7, isn't it? So this is no longer a true binary number. This is the 5 bits we have are these, but this has to be coded as 7. So it is no longer a simple binary scheme. And I mean, you can actually quickly see how you can decode this. See, one way to look at this, let us follow the trellis itself, right? So to get to this level, what are we doing? First, what are we doing? We are going up by 8 steps. Irrespective of anything, we are going up by 8 steps, right? So I'll first put plus 8, right? Sorry. So I went up by 8 steps, and then what do? I go by 2 steps if the comparison output is 1, right? So here the output is 1, so which means I multiply this and go by 2 steps, right? Yes. So next what do? I come down, I'll use this color maybe, compare here, sorry, this right, sorry. Yeah. Now I find that the comparison is 0, so I come down by 2 steps. So it's -2, so this basically comes as -2. Similarly, next will also be -2. This will be +1. And if you do that, you will end up with this guy. But you still have one more comparison, right? So right now we are here. The last comparison we are doing, and that output is also 1. And eventually we end up at this level. I mean, strictly speaking, if this is 7 and this is 8, what is this level? 7.5, right? So strictly speaking, for the last step I come by 0.5. So this will be 7.5, but you want to decode as 7. What do? I mean 7.5, I want to make it to 7. What do? I mean, okay, not floor. I just subtract 0.5 in this case. Okay. So this is how we have to decode. So if I were to generalize this, so first step is always 8, and then 2 times. I either go up or down by 2 times. So that is basically 2 b1 minus 1. If b1 is 1, I'll do plus 2. If b1 is 0, I'll do minus 2. Okay. So similarly 2 times 2 b2 minus 1, 2 times 2 b3 minus 1, plus 1 times 2 b4 minus 1, and the last one is 0.5. So plus 0.5 times 2 b5 minus 1, and I have to subtract 0.5 again. This is how I'll have to decode. So now we'll also see what will happen if I made a correct decision. So this as we saw, even if we make an error, we are able to correct for it. Let us say we made correct decision in the first comparison. Let us see what we get. So this is the first level. If the comparison I made has no error, where do I go? That will be 0. Again up, and then it is same. So let's see. So this is the output I should get is 0, 1, 0. Is that okay? So first is 0, 1, 0, 1. So let's try to decode this and check. So according to our scheme, the first, let me push this slightly to the right. Yeah, 1 second. It's okay, screw that. First is 8. Let me write the weights 8, 2, 2, 2, 1. So what do I do next? Minus 2. Minus 2 plus 1, and then this is 0.5, remember, and then at the end I am subtracting 0.5. So here 2 goes, 0.5, 0.5 go. So as you see here, 2 5-bit data are decoded as the same number here. So do you think it makes sense that I have the same number can be represented as 2 5-bit codes? Do you think it makes sense in this scenario? Here I see that the same number 7 can be represented in 2 different ways in our scheme. I am asking, do you think if this makes sense?
This is not, we are not taking it as a binary.
Yeah, so
Can you base the base of your?
yeah, it is not like we are not changing the base here. I mean, if you have to follow a true base scheme, it should go as exponents of that base, right? That's not happening
We
here.
our own rules.
Yeah, I mean, see, logically speaking, it should make sense because the whole point of arriving at this scheme was if I make an error in one of the bits, I should still get the correct. So, which means even if there is a flip in one of the bits, the final data should be same. So, it makes sense that the same final code is represented as 2 different 5-bit strings. Okay. Great. So now let's look at one other thing. Erase this. Okay. Let's see if we can erase this like this. Yeah. So as we saw in the example, if the input is somewhere here, even if I make a wrong decision, I can come back to the correct output code. So, so that should make you ask the question, right? How much is the error I can make in this comparison that I can still get the correct output? That is, see, right now if the input is here, we know it is okay. The question is, let us say if the input is somewhere here and I make a wrong comparison, will I still be able to come to the correct code? Or what is the maximum error I can make? That is, how far from this reference voltage my input can lie, that even if I make an error in that case, I will still be able to come back to the correct code. Sorry? We have redundancy, correct, right?
We don't have redundancy for all the
Yeah, so no, this is the first step, isn't it?
That the given red line is input, right?
Yeah, red line is, I mean, we know that we have redundancy in the first code, which means I can make an error here. But how much is the maximum error I can make? That's the question.
Depend on the time constant.
No, let's say, forget about time point. Let's just look at this. It's a mathematical question I'm asking now. Right? I know that if my input is somewhere here, I'll be fine. So, how low the input can be that even if I make an error, I'll be able to get the correct output. Let's say if the input is here, and in the first comparison I make a wrong decision, will I be able to come?
How can I make wrong decision?
Let us say you make, right? I mean, let's say you make a lousy comparison. Now you have redundancy, which means you don't have to worry about time constant, right? See, now you have something to correct for an error. So go make an error. If that helps you save power, right? So the question is how much of an error I can make? How do you find? It's simple logic question, right? How can you find it? It's nothing to do with circuits, plain logic.
It's like how many steps I can count down.
Yeah. So let's look at it. I think you get it. So let's say if I know that for a fact the first step I'm going to make an error. So I'm going to go up in the wrong direction. Now let us see how low I can come down. That's all.
Last, the sum of last.
Yeah. So we'll come this point. So basically I can make an error till this much. Right? So that's basically 4 LSBs. So even if my input is in this range, and even then if I make an error, I'll still be able to correct for it. If it is any lower below that, I'll not be able to. And I mean, this doesn't, it's not that we can make error only in the lower direction, we can also make it in the other side. That is, we just draw that also. Say my input is in the positive half, and then I make an error by going down. Then also I'll be able to correct for it, right? So even then, let us say I make an error by coming down. Let us see how much I can correct for it. So as long as my input is in this range, I'll be okay. So that is again 4 steps. Okay. So the total redundancy I can have in the first step, it is 4 in the downside, 4 in the higher side. So 2 times 4, 8 LSBs. Okay. So let's now try to generalize it, right? So how did we come to this? So I know redundancy is going to be 2 times the margin I have in one of the sides. So how do I find it? So I went down by 2 steps. So again, if I call the weights as, yeah, let me write it, W2, W3, W4, W5. So it's going to be minus W2 and then W3 plus W4 plus W5. So there is one other thing you have to do. So here if you see, this is basically 2, 2, 2 and 1, right? If I do this, how much I get? 3. But how much I have? 4. So I have to actually add plus 1. Go and think about it. Okay. So again, if I were to generalize it, for the first step, the redundancy, I mean, let's say I do for the kth step directly. So tell me what is the redundancy I can have for the kth step? It is 2 times k plus 2 to the last step. Hold on. Student WI and plus 1. So this is the amount of redundancy I can have in the kth step. Okay. So let's quickly see how much is the redundancy have in the second step, right? So maybe I can copy paste this. So this is the second step. So let's see how much is the leverage I have. So first let's calculate from our thing, right? So our weights are 8, 2, 2, 2, 1. So what is the redundancy? 2 times. I'm checking for the second step. The wrong step I can take is how much? What should I subtract? minus 2, that is the wrong. Corrective steps is 2 plus 1, and then I am adding 1 here. So how much is this? 2 times 2. Okay. So in each side I have a redundancy of 2 LSBs. So let's check that. So this is the second step. Let us say I make an error by coming down. The maximum I can go up is till this much, and that is basically 2. Similarly on the bottom side I'll have 2. Great. And I mean, the example I showed is just one way. You can introduce redundancy in other ways also. So for example, let us say this is a conventional binary weighted scheme. Right now I split this as 2 plus 2 and then got 1. I could also have done this, right? So I could have done probably 2 plus 1 plus 1, and I could have done 8, 2, 2, 1, 1, 1. So this way I'll have a total of 6 steps. So 2 redundant steps, right? I can also do other combinations. The 8 I can split as 6 plus 2, and then let's say it's 4, 2, 1. I can make it as 6, 4, 2, 2, 1. There is possibility. Or I can also take 8 as 6 plus 1 plus 1. Let us say 6 and 4 I write. I add this 1 with 2, I make it 3, right? And then 1 and 1. So you can have any possibilities, and you have to choose it based on the fact that, I mean, you have to choose it based on how much redundancy you have in each step. You know how to calculate it, right? So with different kind of redundancy schemes, the number of redundancy, the amount of error you can make, and the number of places where the redundancy is. Here you see that we have redundancy in both steps, right? So the number of redundancy you have and the amount of redundancy you get will be different in each scheme, and it will also change the way in which you are decoding. Here you saw the decoding has to be done like this. Maybe if you do some other scheme, the decoding might be a little bit more complex. So it's all a trade-off. There is no one clean choice. You have to choose it based on your stuff. And actually, if I have to put the timeline in perspective, right? As I mentioned, or before that, this way of redundancy, wherein you keep the total number of capacitance. That is, we kept the total weight to be 15, right? We kept the total weight to be 15 and distributed this weight as multiple steps. So this way of redundancy was introduced not so, I mean, it's quite recently introduced in 2015 by Liu. He's the same guy who introduced this monotonic DAC switching. And again, if you look at the timeline, right, the SAR, as I mentioned, has been known for several years, right? In 2005 to 6 is when the asynchronous operation was introduced. And then it all exploded. The interest in SAR design exploded. 2010, monotonic switching was introduced. And the scheme that I have shown for redundancy was introduced in 2015. So it's all actually quite recent. And remember that this is all possible because we have this asynchronous logic, some clever digital circuitry, and also simple.
This was available before also, right?
Which
The
one?
idea did not come. These are things you made the circuit. Things were there way before, right?
Which circuit?
D flip flops and that, the whole circuit.
People knew D flip flop. I mean, it's not like the asynchronous part was done very recently, 2005, around that time. Till then, people are all doing the synchronous SAR by feeding a high frequency clock. So that's why SAR was never used in high speed. It was all low speed and no one really was working in SAR. But after this asynchronous business was introduced, there was no limit to SAR, right? You can use it in all ultra high speed ADCs. So the research in SAR has exploded a lot, and that's why you see a lot of work going on. We don't have a lot of time. Let's stop here. Yeah.